We've been exploring space-time diagrams over the last number of video lectures and seeing how they can help us visualize and gain some insight into some of the key things about the special theory of relativity, such as time dilation, length contraction, the Lorentz transformation, and so on and so forth. And so in this video lecture, we want to consider this idea of regions of space-time and the so-called light cone. We'll get to that in a second, but before we do that, I want to go back to something we were doing in the last video in terms of representing two sets of coordinates, two reference frames really on the same plot. So remember how we did this? We didn't do this one. We'll get to that in a second. But we did this where we had, again, Alice observing Bob going by in a spaceship to the right in the positive x direction at velocity v. And clearly we could have two separate coordinate systems. We could have Alice's, we could have Bob's, just as we normally do at right angles. But we showed last time that we can actually, or last couple times, showed that we can actually put both coordinate systems on the same plot. And we did that by using the Lorentz transformation to take points from Bob's coordinate axes and plot those transformed onto Alice's coordinates, leaving Alice's the normal right angle coordinates we have there, or the axes, the x and t axes for Alice. And we showed that you end up with something at an angle here. We also made the point that you have, of course, lines of same location and lines of simultaneity, lines of same time. And so on Alice's plot, the lines of same location are the vertical lines represented by the tick marks. And the lines of same time, lines of simultaneity, are the horizontal lines parallel to the x sub a axis, again represented by the tick marks. Meaning, of course, anything on a horizontal line in Alice's frame of reference, everything on that line, any space-time event that occurs on that line is simultaneous to Alice. And then any point on a vertical line, or any set of points on a vertical line, are things that occur at the same location, though at different times, as time goes on there. And then we put Bob's axes on there, and it's important to see they're parallel again. In other words, Bob's lines of same location, get the green thing here, are these lines here. Here's his t sub b axis. So this is the line of same location for x sub b equals 0, of course. And then the line for x sub b equals 1, 2, 3, and then negative 1, negative 2, negative 3, and so on and so forth. And then the lines of same time, simultaneity, are oriented parallel to the x sub b axis, because this is the line for t sub b equals 0. Anything that occurs at t sub b equals 0 is along there, and t sub b negative 1, negative 2, or 1, 2, 3, and so on and so forth. So we can actually take a given space-time event, say represented by this red dot here, and in Alice's frame of reference, I've drawn it such that it looks to be about 2.5 over, and then went about 4 up, maybe not quite 4 up, and so that would be the location about 2.5, someplace in there, x sub a 2.5 and t sub a 4. And if as we started doing, we're using units of c being 1, so light years per year, light seconds per second. So this could be maybe, in terms of location, might be 2.5 light years over, and time of 1, 2, 3, about 4 years, or 2.5 light seconds over, time about 4 seconds. And that would be in Alice's frame, but in Bob's frame, according to his coordinate system, we'd see that here's his line of same location. So we go up there from that tick mark, and we see it's approximately 1. And then the parallel line, parallel to the xb axis for the line of simultaneity, looks like about 3, just roughly. This isn't quite drawn exactly to scale there, but you can see that, so in Bob's reference frame, he would measure that space-time event as xb equals about 1, it looks like, and tb equals about 3. Okay, again, these are approximations there. And then for Alice, she would measure that same space-time point, as we noted. X sub a, she'd have x sub a equal, we'll just call it 2.5, and we'll just call it 4. T sub a equals 4. So we see they'd measure different coordinates, of course, And we could transform between those coordinates using Lorentz transformation. Now, my numbers might not quite work out, because I was just eyeballing them there for an actual transformation, but that's the idea. A single space-time event, the event's not changing, it's the same thing. It's a flash of light that occurs someplace in space and time, someplace along the x-axis, because we're doing this in one dimension for the x-axis, and Bob measures it to occur at x sub b equals 1, time equals 3 on his clocks, on his lattice of clocks, whereas Alice measures it at x sub a 2.5. And time for her lattice of clocks at 4 seconds or years or whatever units we happen to be using there. And we did a little bit more with that to show how we could see time dilation on there and a little bit of length contraction and so on and so forth. So that's just a reminder of how we can put both coordinate systems, both frames of reference really on the same plot and get some use out of it in terms of analyzing things with the special theory of relativity. You might ask, what if we'd done it where we did it sort of from Bob's perspective, and then Alice was moving, which Alice then would be moving to the left. So if we consider Bob to be stationary in his frame of reference, and Alice moving negative v to the left, what would our combination plot look like? We're not going to try to prove this. We'll just say, here's what it looks like, and that's what this is here. So notice we've drawn the green coordinates, Bob's system here, as x sub b, t sub b in our normal 90-degree right angle configuration. And when you have the reference frame moving to the left, negative v, then it turns out, and you do the Lorentz transformation equations, it turns out Alice's axes would be at these angles here, sort of tilted away from Bob's axes. But the concept is the same here. In other words, here is the same event on this plot. And note that it is at roughly, in Bob's coordinate system, his reference frame, it's at 1, 3. So 1, 2, 3, there's the red dot, 1, 3. Same thing we got up here. Okay? And on Alice's, for Alice's plot, very roughly here we can see, okay, what's x sub a? Well, 1, 2, it's about 2.5 there. There's the parallel. That's the line of same location on Alice's plot there. And again, roughly at 4, because this has to be parallel to this. So when you're using these skewed axes, as we've done a couple times before, when we just introduce them very basically as, hey, we could do something like this, remember that you don't just measure over at right angles. You have to use the angles of the axes to indicate the location of a given event in this case. So again, same event from either Alice's or Bob's perspective, and in either way of plotting there, you will get the same results, assuming you've drawn your diagram roughly correctly there. Okay, so that's just a brief reminder and a few new things about sort of if you did it from Alice's frame of reference, or really if you had a situation where the moving frame was going to the left, then you get something like this. Although typically, it just, for whatever reason, this is more standard. We like to have things going to the right and deal with this system there. One other note here that will become important in our light cone is, remember, when we take the units to be light years per year or light seconds per second, then c has the value 1. And therefore, if we were to plot on either of these plots, if we were to plot a light beam traveling out from the origin at velocity c, of course, then its slope would be 1. It'd go 1 light year in a year. Okay, its rise over run would be 1. Or its velocity, the run over rise, would also be 1. So it'd be, you could do 2 light years traveling in 2 years. So 2 light years per year would be a point. Let's just put it in here and get it in here, roughly speaking, right there. Okay, 3 light years, and let's do 1 light year in 1 year is going to be about right there. And roughly speaking, 3 light years in 3 years is going to be up here someplace. My tick marks are a little off, but remember what you get here. That's way off, actually. Just put it over here. You get a line at a 45-degree angle for the speed of light, traveling in that direction and actually going down that way as well. So that is a light beam traveling in the positive x direction. Remember, it's easy to get confused with all the angles here. Everything is happening just along the x-axis. And we're just plotting it, the motion through time here. So this represents a light beam going along the x-axis, traveling at velocity c, and this tells us how far essentially it goes in a certain amount of time at the speed of light, 45-degree angle. So it splits not only Alice's axes here, but it splits Bob's axes as well. They're symmetrical across that 45-degree line representing the speed of light, or an object traveling at the speed of light, really not an object, a photon, a light beam traveling at the speed of light there. You can also, of course, have the light beam going in the negative v direction and look something like this at a 45-degree angle, and also you can go that way as well. So if it's traveling from here up, it's going in the negative direction. And it works the same on this plot as well. 45-degree angle really splits the axes here, so the light beam goes like that, and same thing here. Okay, so those are the world lines for light beams on our plots, assuming that c is 1 light year per year, 1 light second per second. The world line for a light beam or a photon will always be at a 45-degree angle, either in that direction or the opposite direction here. So having said that and sort of messed up our diagrams over there now, let's turn to this diagram, and you should have already guessed, you probably already have, that really talking about the same thing here. So this is, we're going back just to a single plot, single diagram for a reference frame, time up here, x-axis here. We will again assume that the speed of light is 1. We're representing it as 1, like 1 light year per year, 1 light second per second. Sometimes you'll see this diagram in certain books with, and we mentioned this before, I believe, with CT here, C times T, and that also essentially puts things in units of 1. But we'll just assume that, so we'll assume T is in years, and then X has to be in light years, or seconds, light seconds, etc., etc. So what's going on with this diagram? Well, here's the idea. You can see all the dots we've got, and we've drawn in what's known as the light cone. And we'll see why, you can see why it's called that. It sort of has a cone-like feature, but it represents, from the origin here, where we have dot number 1, point number 1, a light beam traveling in the positive x direction would go like that. That's how we'd represent it. It wouldn't go like that. That's the world line. It literally would be going along the x-axis. And this is its world line through time. If it happened to start in someplace over here, if this is 0, if it started over here someplace and was going that way, then we'd have it starting down here. You know, maybe there's a flashlight or laser right here shooting out the light beam in the x direction, and therefore the world line would be going up like that. And if we shoot it in the other direction, maybe start over here and shoot it this way, then the world line starts here and moves up that way. So the red lines represent the world lines of a light beam. Now the key question here that we want to ask, and this gets into one of the themes for this week that we've been working toward, and that is what happens with cause and effect, and what happens with the speed of light. If you can go faster than the speed of light, we've talked about how you can't. We did some analysis of what happens if you had a light clock, say, moving. If you could get up to the speed of light, what would happen then? Gamma becomes infinite, and so on and so forth. So that hints strongly that you can't get up to the speed of light. But we want to consider some situations now in terms of, specific question here is, if I have an event happening at point 1 here, say anything at all, okay? Can that event affect any of these other events here? Okay? And one way to think about it is, let's just go from 1 to 2. Okay, so note that from 1 to 2 here, if I think about a message or just a spaceship traveling, okay, really, literally speaking, 2 is happening right here on the x-axis, okay, and 1's over here. So could I, in a spaceship, say, get from 1 to 2 in time to affect something happening at that point up here? So it's really at time, at position 2 and time, whatever time we have over here. Well, the key thing here is note that if I were to draw the world line here from 1 to 2, something like that, that world line has a velocity less than the speed of light. Remember how this works? Velocity is proportional to the inverse of the slope of our world line. So faster velocities are like this. Slower velocities are up here. This is the speed of light here. So if I'm going less than the speed of light, I've got to be over here someplace in terms of my slope. So from 1 to 2 here represents a world line of something that is traveling slower than the speed of light. And we know that's possible. So therefore, in theory, yes, if I have a spaceship here and I need to get to position 2 over here in this amount of time here, I can make it, assuming my spaceship is fast enough. It doesn't have to go to the speed of light, it just has to go at some speed less than the speed of light, pretty fast probably, but it will get there. Okay? And so we say, yes, an event at 1 can affect an event at 2. And in fact, if you think about it a minute, any events within this cone here are able to be affected by an event at 1, because again, I could get in a spaceship that was fast enough, and I could travel to point 13 here, which is actually just on the x-axis. I really wouldn't have to do any traveling. I'm sorry, not the x-axis, the time axis. I wouldn't have to do any traveling. I'd just sit there and wait until 13 came along, 10 seconds later, 10 years later, or whatever it happened to be. So I can get to places like that. Note where I can't get, however. Look at number 3 over here. Okay? If I say, okay, I'm going to get in my spaceship, go as fast as I can, and I'm going to try to get to point 3, which is out here at some position, not position 12, that's just another dot, but some position out here at some later time. To do that, I'd have to have a world line, something like that. Well, I missed the dot there, but at least hit the 3. That would be the world line to get there. And note that that world line has a slope less than the speed of light slope, and therefore it's a velocity faster than the speed of light. In other words, to get from 1 to 3 through space-time, which means traveling both through space and through time, as it were, as time just ticks on, I'd have to have a spaceship that goes faster than the speed of light. So I cannot get there. And similarly for 12 here, note for point 12, it's right on the x-axis, and that's a line of simultaneity if you're in this reference frame right here. In other words, no matter where you are in here, if it's any distance away from you, to affect something, you'd have to have instantaneous communication, right? And that's going to be impossible. Same thing over here for number 8. If I'm traveling in the negative x direction, I can't get to number 8 in time to affect anything. Okay, I don't have a spaceship fast. I'd have to have a spaceship faster than the speed of light, or be able to send a signal faster than the speed of light. Same thing for 11 here. So in terms of, well, actually, let's go back to not 11, not quite yet. We'll get to that in a second. So in terms of the upper part of our diagram here, anything within this light cone here, I can reach in time. Anything outside the light cone, any point up there, is too far away from me. Note, x8 here is farther away than 9. We'll get to that in a second. Certainly 3 here is farther away than 2. And so I don't have anything fast enough to get there. Okay? What about these points on the bottom? Well, the question there is not what something at point 1 can affect these points. These are earlier in time than point 1. So here the question is, can an earlier event affect what's going on at point 1 here? Well, again, same idea. If a space-time event at point 6 happens, and I want to affect something at 1 here, maybe I'm going to get in my spaceship and travel really in the x direction over to here, and also through time to that point, and deliver a message or something. Maybe there's a big vote in the Congress or Senate or Parliament or something like that, and I want to deliver a message to say, vote this way. Well, I can make it there in time to deliver that message and affect the event there if I'm at 6 here, because that world line to get from there to there has a slope that tells me the speed is less than the speed of light. Same thing for 5 here. If I'm over here, I'm traveling in the positive x direction to get there. I can make it in time to get there. 10, however, if I'm over here, I'm too far away in terms of the x direction to be able to get to that point in time and space without traveling faster than the speed of light. This represents a world line that is of an object traveling faster than the speed of light there. Let's see, what else? We talked about 12. Okay, that's instantaneous with point 1, so clearly can't make it there. Talked about 3. Mentioned 13. You just sort of sit there and wait for 13 to occur in time, because this, again, is x equals 0 here. 11 over here, again, just like 10 really, it can't get to 0.1 in time. It has to go faster than the speed of light. What about 9 and 4? Notice, and also 7 down here, note that they are right on the light cone. Okay? What that means is that if I'm at 0.1 and I want to affect something going on at 0.4, if I travel at the speed of light, I can just get there in time. And same thing over here, going the negative x direction, I'll be able to get to 0.9 in time. And then down here for 0.7, if I want to influence something at 0.1, I have to travel at the speed of light. So I'd have to send a laser beam or something, or a light signal with a message that would get there in time. So, I guess get a little messed up there, but again, the idea is the light cone, and you have different regions of space-time that it defines just by these 45-degree axes representing the world lines of a light beam. And we have some other names for this as well, and also it allows us to go back and revisit the invariant interval. So let's, we don't need this here. Let's introduce this again. Okay, so again, remember the questions are, I'm at 0.1 here, and if I'm at 0.1, can I influence something later on in time and at another point in space? Or if I'm in time before 0.1, where I am, can I get a message there or travel there in time to influence something at 0.1? And so we have 3 names for these situations, because if you think about it, I can either get there in time, whether I'm going to 0.1 or to another point. So that's something, and we call that a time-like interval. A time-like interval. And really the key question here is, we'll write it as, do you have enough time to, you could say, really just to make the distance. Let's put it like that. And this should be a little intuitive if you think about it, because in our everyday lives we think about this a lot, perhaps. If you drive a car, or even if you're taking a bus or a train or something, you think, I have to travel a certain distance, and I have a certain amount of time to do it, and do I have enough time to get there, given the distance and the speed that I can go? So that's really what we're asking here. Do I have enough time to make that distance, given the parameters I'm dealing with, whether car or walking or however I'm going from one space to another point through time as well, because as maybe I'm walking, time is ticking on too. So I'm traveling through both space and time that way. And a time-like interval is such that, yes, you do have time to get there. Okay, and I'll write remember our invariant interval equation? C squared t squared minus x squared equals a constant. And it turns out we're not going to try to prove this rigorously or anything. We're just going to state it. And that is, if you have a time-like interval, what that really means is that this invariant interval, c squared t squared minus x squared, turns out to be greater than 0. And you might say, well, why? Well, we can motivate this a little bit, actually, because this means that, if you do a little bit of the algebra here, this means c squared t squared is greater than x squared. Okay, just moving the x squared over. Or if we take the square root and everything is positive here, we can say that c, t, in general, is greater than x. Now, what does that mean? This is essentially, c is, of course, the speed of light. C, the speed of light, times a certain time. This is the distance that light can travel. Okay? And I should say that light does travel in a given time. If I say, okay, I've got 10 seconds, I've got 10 minutes, how far does light travel in that time? You just do c times t. That will tell me how far light travels. And if that's the ultimate speed limit, if that's the fastest I can get someplace, I know if I have a certain amount of time to get someplace, ct is the fastest I can go. You're like, of course, you can't quite go to ct, but I can get pretty close to it. If that distance the light can travel is greater than the distance I need to go, then yes, I can get there, or at least a light beam can get there in that time. So this is essentially saying the distance light can travel in that certain amount of time I have is greater than the distance, and yes, it's reachable then. I have enough time to make the distance in that case. And so that's called a time-like interval, and again is represented in a diagram when you have things points within the light cone that you can travel either at the speed of light to get to point 4 from point 1, or point 9 from point 1, or less than the speed of light to get from like 1 to 2, or down here from 5 to 1, or 6 to 1, or 7 to 1 at the speed of light. Well, let me back up there. We have a special name for the speed of light cases here. So the time-like interval ct greater than x is, for example, for 5 and 6, and 1 and 2 there. Now, so that's the time-like interval. And next one is actually called a light-like interval. A light-like interval. And as you might guess, just from the name, this is when you do have things going at the speed of light. In that case, you have the invariant interval c squared t squared minus x squared equals 0. And pull the x squared on the other side, take the square root, and from this you get that ct equals x. And as we were just talking about, if ct is the maximum distance anything can go in that given time, because this represents the speed of light traveling over a given time, that means the distance x is exactly equal to that maximum amount of distance I can cover. Okay? In other words, do I have enough time to make the distance? If that distance is reachable just barely by something going the speed of light there, we call it a light-like interval. And so in our diagram, that would be like going from 1 to 4. The only way to get from 1 to 4 in space and time is to travel at the speed of light. And again, really, you're going out here to position x, but you only have this much time to do it. And you have to travel that much time, or that much distance. To get there, you have to travel at the speed of light. And that's called a light-like interval, or from 1 to 9, or from 7 to 1, going that way. Those are light-like intervals. So a given point here, if it's within this cone this way, or down here, it's a time-like interval from this point to that point. If it's on the light cone, it's a light-like interval. In our third case is a space-like interval. Third case, space-like interval, and just from what we've done, you can guess what this one is. It's c squared t squared minus x squared is less than 0. And the same analysis then tells us that ct, the maximum distance we can cover in terms of what light can cover, is going to be less than the distance x, in terms of the location of where x is. In other words, this is saying that, back to the question, do we have enough time to make the distance? No, because the maximum speed we can go is the speed of light, and that means we can get a distance ct away, or a light beam can get a distance ct away from where we are. But if that's less than the distance that needs to be traveled, then you can't get there. And that's called a space-like interval, because space, the space coordinate there, dominates over the time coordinate. Light-like is when space and time coordinates are equal in a sense, and time-like means the time coordinate dominates over the space coordinate. And so a space-like interval would be represented by, like, from 1 to 3 here. That is a space-like interval. I can't get from 1 to 3 in my spaceship or even a beam of light. Cannot get from 1 to 3. It's too far out here for the amount of time I have. Or, again, 1 to 8 over in this direction. To get over here in the amount of time I have, don't have enough time. Same thing from 11 to 1. Starting at 11, can't get to 1 in time, or 10 to 1 going that way. Okay, so time-like intervals, light-like intervals, space-like intervals. This is another way to see sort of the limitations that the special theory of relativity puts on us as we travel, in a sense, through space and time. And in the next few video clips, we're going to explore some other aspects of this.